Today on Macaulay Math, we're talking related rates. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, Lesson 12 on related rates. Our goals for today. We're going to use implicit differentiation with related rates. We're going to find a related rate, and we're going to solve related rate problems. Related rates is an introduction to an important branch of calculus known as differential equations. They are also one of the applications for which calculus was created. What is a related rate? Well, let's start with a demonstration.
Let's say that you are a rocket scientist, and you want to know something about how your rocket is accelerating. We know that force is equal to mass times acceleration. In a rocket ship, force is generated by burning fuel inside and expelling the mass out of the back of the rocket. If you have your engine throttled up to its maximum output, then the force is a constant. Since the force is a constant, and the mass of the rocket is changing by expelling a portion of the mass from the back of the rocket, the acceleration must also change. As the mass of the rocket shrinks, the acceleration of the rocket must increase. The mass and acceleration of our rocket are related, and the rates that these two quantities are changing can be modeled by calculus in a measurable way. Related rates were created in an attempt to model these relationships. Related rate problems are nothing more than an application of implicit differentiation. As an example, the volume of a cube is expanding at a rate of 15 centimeters cubed per minute. At what rate is the length of the side expanding when the side is 10 centimeters long? How implicit differentiation applies. And so we want to talk about how implicit differentiation applies to this problem. First, we know the rate that the volume is changing. Second, the question asks the rate at which a side is changing. These two rates are related by the equation for the volume of a cube. Both of the rates are derivatives with respect to time, but the volume equation is a volume as a function of length of the side. Neither of those two variables are time. So in this instance, we're going to have a function that has two variables in it that has nothing to do with time. If we derive two variables with respect to some other variable, we have to go through implicit differentiation. Before we get started, let's talk about some guidelines for solving related rate problems. Again, there are no hard set rules, but these guidelines will give you an idea of some of the things that you might want to try to solve the problem. First, identify the given quantities and all of the quantities that need to be determined. Sometimes you'll have problems where you may not be given all of the variables, but if you use the equations given to you, you may be able to solve for some unknowns and make the problem easier. Write an equation involving the variables whose rates of change are either known or to be determined. Number 3, using the chain rule, implicitly differentiate both sides of the equation with respect to the common rate variable. This is usually time. Number 4, after completing step 3, substitute into the resulting equation all the known values for the variables and their rates of change, then solve for the required rate. Let's complete that first example. The volume of a cube is expanding at a rate of 15 centimeters cubed per minute. At what rate is the length of a side expanding when the length is 10 centimeters long? First, we know a few things. Let's make a list of those things. First, we know that the change in volume with respect to time, or dV over dt, is 15 centimeters cubed per minute. The question asks, at what rate is the length of a side expanding? So the question asks us to find ds over dt. Since s is that defined variable, we're trying to find that when s is equal to 10 centimeters. One thing that I see is that I have no value for v, but I could possibly calculate that. In this particular instance, that volume is not necessary, and we'll see why right here. If I take that volume equation, v equals the side cubed, and I do the derivative of that formula with respect to time, the derivative of v with respect to time, since it's a value that has no exponent, is just going to be dv over dt. The derivative with respect to time of s to the third will be 3 times s, now squared, times ds over dt. In this particular instance, I can find ds over dt, the value that I'm looking for, by just having the value for dv over dt and s. I have 1, 2, 3 variables. I have 1, 2 values to plug in and 1 to solve for. So let's solve for ds over dt. And that'll give me ds over dt is equal to dv over dt, all divided by 3s squared. Here I will substitute the known values. We know that dv over dt is 15. We know that s is going to be 10. And so if I simplify that, I'm going to get 15 over 300. And if I am not mistaken, 15 goes into 30 twice. So I'll have 1 over 20 centimeters per minute, which is pretty slow. A second example. An airplane leaves an airport at 12 p.m. flying due north at 300 miles per hour. A second plane leaves the airport at the same time flying due west at a rate of 400 miles per hour. After 3 hours, at what rate is the distance between the planes changing? Now, as a note, we have to say that there is a more elegant solution using vector math from physics. But for the sake of this lesson, we're going to use related rates to show that related rates work and are a viable option. So right off the bat, this direction is north, and our first plane is traveling due north at 300 miles per hour. And that our second plane is down here traveling due west at 400 miles per hour. They want us to figure out at what rate is the distance between the planes changing. So they want us to determine what dA over dt is. All right, so the first thing that I want to do is I want to identify the quantities. I know that the change in the distance north with respect to time is 300 miles per hour. I know that the change going west with respect to time is 400 miles per hour. I do not know what dA over dt is, but that is what I'm looking for. I also do not know what the distance north is, what the distance west is, or what the distance between those two functions is. If you recall from physics or one of your earlier classes, that the velocity equals the distance divided by the time, and we could conclude that the distance is the velocity times the time. Since these are traveling north and west, we can calculate that n value by saying that it is traveling at 300 miles per hour for 3 hours, meaning that it has traveled 900 miles. And I can put that quantity in. We can say that it has been traveling west at 400 miles per hour for 4 hours, meaning that it has traveled 1,200 miles. Let's write that in. A can be found using the Pythagorean Theorem. A squared is equal to n squared plus w squared. In this particular instance, we will have a squared is equal to 900 squared plus 1,200 squared. Thus, a is equal to the square root of 900 squared plus 1,200 squared, which turns out to be 1,500 miles. So A is 1,500. So if we write an equation that involves the quantities, so now we've found all of the values. Let's write an equation that relates the variables. Let's say that n squared plus w squared is equal to a squared. That's just the Pythagorean theorem. We're going to derive this with respect to time. And we know to do that because we have rates of change with respect to time. So d, move that up, d over dt of n squared plus w squared equal to a squared. So for each of these terms, I'll have 2n times dn over dt plus 2w times dw over dt equal to 2a times dA over dt. Now this is the value that I am looking for, and I have quantities for all of the remaining variables. I can plug in the known values, and so I will plug in, I'll have 2 times the n is 900 times the rate at which n is moving is 300 plus 2 times the distance for w, which is 1,200, times the rate at which w is changing, which is 400 miles per hour, equal to 2 times the 1,500 times dA over dt, which is good because I have numbers for all of the variables except for the one that I'm looking for. So I can solve for dA over dt. And so the first thing I want to do is I'm going to simplify this. If I multiply 2 times 900 times 300 plus 2 times 1,200 times 400, 1,500,000, and then 2 times 1,500 will be 3,000. Divide by 3,000. That'll give me dA over dt equal to just 500 miles per hour. For our next example, a trough 12 feet long has ends made up of isosceles triangles that have bases 3 feet across and have heights that are 4 feet. And we're going to look at this diagram and we're going to see this, that we have this is the trough, and then this right here will be the end of that trough. If water is being pumped into the trough at 2 cubic feet per minute, at what rate is the depth rising when the depth is 2 feet high? All right, so right off the bat, we need to label a few things. Let's call this thing right here the height, and our height will be our depth. All right, and then we'll call this the base. And you'll notice that in this particular trough, it has a length here of 12 feet. Now, if I'm dumping water into that, as the water goes up, the depth is going to change. And as the water goes up, the length of the base is going to change. The length of the trough will always remain a constant 12 feet. So in this particular instance, this length of the trough is always going to be a constant 12. Now that's going to help us when we talk about the equation for volume. In every instance, the volume of a right solid is going to be the area of the base times the length of that particular right solid. And that's what we have here. We have a right solid that has a base that is a triangle with a length of 12. So the volume of this particular trough will be V equals the area of the base, which will be 1/2 the base times the height of this triangle right here, times the length. Now, right off the bat, because this is a constant and will not be changing, we can simplify this and say that it is 1/2 times the base times the height times 12, which will give us 6 base times the height. All right, so already we've simplified this a little bit and we've gotten rid of one of the variables. We can do the derivative of that implicitly, but we would still have to do a product here. I think that we can simplify this even further into a single variable if we use similar triangles from geometry. As the water fills up this trough, it will always be a similar triangle to this trough triangle that has a base of 3 and a height of 4. So what we can do is we can say that the base of the triangle to the height of the triangle is going to be equal to 3/4 as a proportion. Now again, let's go back and let's see what they're asking us to solve for. At what rate is the depth rising when the depth is 2 feet high? Well, our depth here is the height. So what I want to do is I want to solve this for b. And what I'll do is if I get b alone, I'll have a function in terms of h. I can substitute that in for b for this function here, and then I'll have a volume equation in terms of height only, the variable that I am looking for. So let's do that. I'm going to cross multiply, so I'll have 4b equals 3h. And again, we're trying to solve for b, so we're going to divide by 4. And that'll give us b equals 3/4h. All right, so here we're going to take that and substitute and so I'll have v equals 6 times 3/4h times h, which will simplify down to 9/2 h squared. Now, that is actually not too bad because now I only have one variable. This thing we want to derive with respect to time. So d over dt of v equal to 9/2 h squared. All right, so if I do that, I'll get dv over dt. 2 times 9/2 is going to be 9, and then h now to the first times dh over dt. Now, look what we have. If the water is being pumped into the trough at 2 cubic feet per minute, so my dv over dt is 2 feet cubed per minute. At what rate is the depth rising? So dH over dt is unknown when the depth is 2 feet high. Well, notice if I plug in, I'll have 2 there. I'll have 9 times 2 there. dH over dt is left. That's what we're looking for. If I solve for dH over dt, I'll get dH over dt equals 2 over 9 times 2. The 2's will cancel, and I'll get 1/9. And the units that we're talking about feet. So we have feet per minute. We know that because the volume of the water being pumped into the trough is 2 cubic feet per minute. All right. So there is our answer for A. Now for B, it says if the water is rising at a rate of 1/4 inch per minute, when the height is 2 feet, what rate is the water being pumped into the trough? So in this case, they give us that dH over dt is 1/4 of an inch per minute, and they keep our height at 2 feet, and they want to know at what rate is the volume changing. Now, the only issue we have here well, that's easy because 12 inches equals 1 foot. So if I have to change this from 1/4 inches per minute, it very easily becomes multiplied by 12. I'll get 1/48 feet per minute. And now I can use that same equation that I got right here. I can still use, and we should put B here to denote that we have a second one. But I can use that same equation that we had, dV over dt equals 9HDH over dt. And now it's just a plug and chug. 9 times 2 times 1/48. When that reduces, we will get 9/24 feet cubed per minute. All right, there's our part B. Last one. An airplane flies at an altitude of 5 miles towards a point directly over an observer. The speed of the plane is 600 miles per hour. Find the rates at which the angle of elevation theta is changing when the angle is A, 30 degrees, and B, 60 degrees. All right, so let's write down some things that we got. We know that this is 5 miles, and we know that this value is changing at a rate of 600 miles per hour, and we know that this is going to be our theta. We have an airplane right here. Put a wing on it. I know that's not great, but it's good enough for this diagram. Find the rate at which the angle of elevation is changing. So we are tasked to find d theta over dt. All right. So let's see here. So since it's calculus, it's a good idea to change degrees to radians. And that's an easy change. 30 degrees is pi over 6 radians. And 60 degrees is pi over 3 radians. And we may not need that, but it's just a good idea to do it. If I call this side A and I call this side B, we know that B is 5. We don't know what A is. We may have to calculate that. And we know that dB over dt is a constant. So it's always going to stay 5 miles up. So the change in the height is always going to be 0. And dA over dt is going to be 600 miles per hour. So we'll see what we got. And if we have these two parts here, and this angle theta, this is my adjacent side, this is my opposite side. So it makes good sense that the equation that we're going to use will be tangent. And we know that that is going to be the tangent of theta is equal to the opposite side B over the adjacent side A. Now, the good news is B is a constant. And we can plug that in. So the tangent of theta will equal 5 over A, which will be just equal to 5A to the negative first. So already we've reduced this function down to only 2 variables. That actually makes things very nice for us. And I think at this point what we'll do is we will derive this with respect to time. And so if I go d over dt, tangent theta equals 5a to the negative 1, we will get, let's see here, the derivative of tangent is secant squared theta, and then we have to multiply that by d theta over dt because we're doing an implicit differentiation, and then we'll go negative 1 times 5 is negative 5a to the negative 2 times the derivative of a with respect to t. So now what we're going to do is we're going to solve for d theta over dt, and we know that because that's what it asks us to do, find d theta over dt, so we have to refer back to the original. But first, let me recall that secant theta is equal to 1 over the cosine of theta. And it's not a big deal, but it's going to make things a little bit easier. So 1 over cosine squared theta times d theta over dt equaling to negative 5a to the negative 2 times dA over dt. And so the only reason that I converted secant to terms of cosine is because now I can just multiply by cosine squared theta, and that'll give me d theta over dt is going to equal to the cosine squared theta times negative 5a to the negative 2 times dA over dt. All right. So the good news is I know my 2 values for theta. That's good. I know my dA over dt. The problem is I don't know my values for a. All right. Well, that's not too bad because we still have right here, we have that the tangent of theta is 5 over a. And so since I have to calculate for a anyway, the tangent of theta equals 5 over a. A will equal 5 over the tangent of theta. And so my 2a values, when theta equals pi over 6 and pi over 3, I'll get a equals 5 over the tangent of pi over 6. And just because I know that this is running long, this value here is approximately equal to 8.660, and a equals 5 over the tangent of pi over 3 is approximately equal to 2.887. Now that I found these 2 values, I can actually plug into this equation. I have values for everything. So for part A, d theta over dt is equal to the cosine squared of pi over 6 times negative 5 times 8.660 to the negative 2, all times negative 600. Now, the reason it has to be negative 600, and I had it as a positive 600 here, let's put that negative in there, is because this length is decreasing. So since the length is decreasing, our rate of change is negative. So if I plug all of this into my calculator, I get 30.002 radians per hour. Now I know that seems like a lot because 2 pi radians is a full circle. So 30 radians per hour seems to be a lot. But remember, it's traveling at 600 miles per hour and we're only talking distances of around 5 miles. So it's traveling pretty fast. So that change is going to be very quick. And then if I do part B, the only thing that changes in part B is the fact that my theta becomes pi over 3 and my distance for A becomes shorter. So d theta over dt will be the cosine squared of pi over 3 times negative 5 times, and then A for this one is 2.887. 2.887 to the negative 2 power times negative 600, which will give me 10.001 radians per hour. All right, that is all I've got. So, the Star Wars fun fact of the day. Ben Burtt created the iconic sound for the lightsaber by passing an extremely sensitive microphone behind a speaker and recording the interference. And if you'd like to see a little documentary on that, you can go to this YouTube station right here and it will show you how he did it. It's pretty cool. That's all I got. Have a good day. Goodbye.